Welcome to our video lecture on uncertainty and stoichiometry. Our objectives for today are to review accuracy and precision. We're going to review sig figs. We're going to outline different kinds of experimental errors. We're going to define and calculate absolute and relative uncertainties, and then we're going to calculate percentage error. Finally, we're going to get to some stoichiometry. We're going to review hydrates and then calculate degree of hydration. So first up, lots of ideas regarding uncertainty. When we're talking about uncertainty, one of the concepts that we like to talk about is if our data is precise, if our data is accurate. In common language, these words kind of mean the same thing, but in chemistry and science, they're quite different. Precision is all about repeatability. If I'm getting the same value over and over and over again, my values are precise. This chunk of data here is precise. This chunk of data is also precise. We're getting values that are very close to each other. Accuracy is all about getting the correct or the right value. These values are accurate. We're right on target. These values are also pretty accurate. They're close to the target. Interestingly, these are not precise. I do not have the same value over and over. The data is quite spread out. Here I have values that are neither accurate nor precise. Our data is crazy all over the place and not close to the target. Of course, our goal is always going to be accurate and precise. Uncertainty is also related to the idea of sig fig, significant figures. We're going to review the rules super quick. Non-zero digits are always significant. Zeros are significant if they are to the right of a non-zero digit and there's a decimal. So zeros to the right and there's a decimal, these guys are going to be significant. Let's practice identifying the number of sig figs in each of these pieces of data. So here I have 20 milligrams. There's no decimal, so the zero does not count as a significant digit. We only have one sig fig in this piece of data. Here, 2,000 milligrams. Again, there's no decimal, and so those zeros don't count. Only that 2 is significant. I have one sig fig. Here, 0.2 milligrams. I do have a 0 to the left of the non-zero digit, and there's a decimal. Zeros to the left are just placeholders. They do not count. And so we only have one sig fig. Again, it's going to be that 2. Here things get changed a little bit. I have this 0 to the left of the decimal and the non-zero digit. It doesn't count. But these 3 zeros to the right of the non-zero digit, there's a decimal. These guys all do count. And so I now have 1, 2, 3, 4. 4 sig figs in this piece of data. This next one, I have 1 non-zero digit, I have a decimal, and 4 zeros to the right of the decimal, to the right of the non-zero digit. All of these are going to count. So now I have 1, 2, 3, 4, 5 sig figs in this piece of data. This one's easy. There's only one sig fig. When I'm looking at scientific notation, all of the digits in the coefficient are going to be significant. Here I only have one digit in the coefficient, so I have one sig fig. Here we have, oh my goodness, 1, 2, 3, 4, 5, 6, 7, 8. 8 digits in that coefficient of scientific notation. I have 8 sig figs. When we do calculations with sig figs, we have a couple of rules. Our rules for adding and subtracting, we're going to find the place value of the last sig fig in each piece of data. We're going to round to the largest place value of that last sig fig in each piece of data. This makes a whole lot more sense when we actually practice it. So in this piece of data, the last sig fig is going to be that 2. It's in the 10th place. In this piece of data, my last sig fig is this 4. It's in the tenths, hundredths, thousandths, 10,000ths place value. Which one is larger? Tenths is larger, so I'm going to round my final answer to the 10th place. 2 is in the 10th place. That 0 is going to not change that 2. So our final answer is about 0.2 milligrams. This next example is almost the same, except instead of having just 0.2, I have 0.2000 milligrams. And so now my last place value is going to be in the 10,000th place. Here I also have the 10,000th place. So I'm going to round my final answer to the 10,000th place, which is right there. So I'm going to keep all of those digits. We're going to round, not even round, just keep that 10,000th place. Our final answer is 0.2004 milligrams. When we multiply and divide, this is a lot easier. We're just going to count those sig figs and we're going to round to the least number of sig figs in our data. So 0.2 times 0.2 is 0.04. I have one sig fig, I have one sig. We're going to keep one sig fig. There it is right there. Remember that zeros to the left of the non-zero digits don't count. They're just placeholders. And so our final answer is going to be 0.04 millimeters squared. Here's a little bit different. I have 1, 2, 3, 4 sig figs. I have 1, 2, 3, 4 sig figs. So our final answer needs to have 4 sig figs. Right now we only have 1. To fix that, I'm going to add some zeros to the right of my non-zero digit. That's going to make all of those zeros significant. Our final answer is 0.04000 millimeters squared. So onto this idea of experimental errors. In uncertainty, we can have these errors. Errors can be either systemic or random. This is an idea that we don't talk about as much in 10th grade chemistry, so it might be new to you. That's okay. So our systemic errors can be related to instruments. If I have a scale that is not calibrated correctly, it's going to give me the wrong answer. That will be an error. My methodology might be off. If I'm maybe measuring the product of a chemical reaction and I'm not letting my reaction come to completion, I'm not going to have the right answer. We're always going to have too little product. If I have personal errors, this could be where I don't know how to use the equipment. Maybe I think I should measure at the top of the meniscus instead of the bottom of the meniscus in our graduated cylinder. Or maybe I'm colorblind and I can't tell when the light turns green. These are all going to give us some systemic errors. Interestingly, systemic errors are going to affect accuracy more than precision. Because my scale is calibrated incorrectly, I'm going to get the same precise, wrong, not accurate answer over and over and over again. Random errors, these are things that happen that I cannot control. We're going to have a lot of accuracy and precision issues. So precision will not stay the same. We won't have precise answers the way we do with systemic errors. Instead, everything's going to be kind of helter-skelter all over the place. So now we're going to look at calculating uncertainties. We have two different kinds of uncertainties that we're going to look at. We're going to talk about absolute and relative. Absolute uncertainties we're going to denote with this delta A. And this is simply the degree of uncertainty according to our pieces of instrument. Relative uncertainty, this is now going to be relative to the measurement. So it's going to be that absolute uncertainty divided by, this is going to be my actual measurement. And I show uncertainty with my measurement plus or minus my absolute uncertainty, and then we're going to add that unit, whatever it might be. So let's look at an example showing absolute and relative uncertainty. It'll make a whole lot more sense with some practice, I promise. So one of our analytical scales might be labeled with an uncertainty of plus or minus 0.0001 grams. That is actually the absolute uncertainty. So that label tells us that we've got plus or minus, with that little bit of wiggle room around the mass, 0.0001 grams. That is the absolute uncertainty. Relative uncertainty, that's going to be the absolute uncertainty divided by the measurement. Absolute uncertainty is here, 0.0001, divided by our value. Our measurement is here on the scale, 0.4253, 0.4253. So our uncertainty is going to be 0.0001 divided by 0.4253. Handy dandy calculator says that's going to be 2.4 times 10 to the minus 4. This is our relative uncertainty. I can change that to a percent if I want to by multiplying by 100. we'll get 2.4 times 10 to the minus 2. We could also turn that into a decimal that's not in scientific notation. We could do our standard notation. It's going to be 0.024. And since these are our percent relative uncertainties, we're going to throw that percent sign at the end. So this is our relative uncertainty, our percent relative uncertainty, our absolute uncertainty. Here's another example. I have a thermometer. It's going to be measuring in degrees Celsius. To find the absolute uncertainty, our analog devices, different from our digital devices, they don't always come with a label that tells me what the absolute uncertainty is. So what we're going to do is figure out what each of our increments is equal to. So in our analog, not digital, analog devices, we're going to figure out the smallest graduation. Each one of those graduations is 1 degree Celsius. We're going to then divide that by 2, and so our absolute uncertainty is going to be 0.5 degrees Celsius. Absolute uncertainty is going to be 0.5 degrees Celsius, half of each of those increments. Relative uncertainty, we're going to take that absolute uncertainty that we just found, divide it by our measurement. So 0.5 degrees Celsius divided by, that looks like about 27.5 degrees Celsius. Do that division 0.5 divided by 27.5 and we get 0.018. This is our relative uncertainty. To turn that into a percent, we're going to multiply by 100. So that's going to make 1.8% our relative uncertainty. So now we're going to add another layer of complexity to our uncertainties. Just like we had rules for sig figs when we did calculations, we're going to have some rules for uncertainty when we do our calculations. When we add and subtract, we're going to find the square root of the sum of the squares of the absolute uncertainties. Nice shortcut, we can also just add the absolute uncertainties and call it close enough. So let's say that I have an initial mass of magnesium sulfate, 2.9982 plus or minus 0.0001 grams. The final mass after heating was a little bit less, 2.7740 plus or minus 0.0001 grams. I want to determine the mass lost. Of course, we're going to subtract 2.9982 minus 2.7740. That is going to give us, that's a 2, that's a 4, that's a 2, that's a 2, that's a 0. So 0.2242 grams. But that plus or minus uncertainty, we have two options. The much better option is to just add those two guys together. So I'm going to add my two uncertainties when I add and subtract. 0.0001 plus 0.0001 is going to be plus or minus 0.0002 grams. This will be my value with absolute uncertainty. If we want to do this method, our other option is to do that 0.001 squared. And we're going to add, because this is the sum, the other uncertainty squared, and then we'll take the square root of that. And that turns into 1.4 times 10 to the minus 4, which is going to be 0.00014, which isn't exactly 0.0002, but they're not that far away from each other. So again, you have two options. You can do this crazy messy thing, or you can just add them together. I highly recommend you just add. Sadly, there's not a good shortcut when we're looking at multiplying and dividing. So our fancy one, we're going to take the square root of the sum of the squares of the relative uncertainties. Our shortcut is to just add, take that sum of the relative uncertainties. Don't worry about the squares and the square roots, but I still have to find relative uncertainty, which is that absolute uncertainty divided by my data, by my measurement. So if I want to find the density of zinc, density is mass over volume. In this problem, the mass is 28.9612 divided by 4.6. And then we do that division, 28.9612 divided by 4.6 gives us 6.3 lots of digits. I'm only going to keep 2 sig figs because I only have 2 sig figs here in my volume. So 1, 2, and my final answer, grams over milliliters, is our density. Our uncertainty, what we're going to do is figure out what are the relative uncertainties of each piece of data. So I have to find relative uncertainty of this guy, which will be that absolute uncertainty 0.0001 divided by my measurement 28.9612. Do that division and we get 3.45 times 10 to the minus 6. We're going to do the same thing for this piece of data, 4.6 and 0.05. Take that absolute uncertainty, 0.05, divided by the measurement, 4.6, and we're going to get 0.0109. So 2 options. We can just add those together and call it done, or I can square each of those, add them together, and then take the square root. Either way, we should get just about 0.0109. So our answer is going to be, and I'm going to round this to also 2 sig figs. So I'm going to turn that 9 into, round that 0 up to a 1 because of that 9. So our final answer will be 6.3 plus or minus 0.011 grams per milliliter will be our final answer. We could have also done the crazy thing where we square and then add and then square root, but we're going to get almost the same thing. Good? So messy. So now we're going to do a slightly easier piece of calculation, percentage error. The tragic part about percent error is you do have to memorize this formula, literature minus experimental divided by literature, all in absolute value bars, and then times 100 to turn it into a percent. So literature value is just what we know to be true, the accepted value. So on the previous slide, we talked about experimental density of zinc. We found it to be 6.3 grams per milliliter. That's our experimental value. Our accepted density is going to be that 7.140. So I'm going to plug this in for literature value in both spots. So 7.140 minus experimental, that's what we found in our experiment, 6.3. There's a point in there, divided by 7.140 absolute value bars times 100, and we're going to get a percentage error of, looks to be just about 0.118 times 100, 11.8, or just about 12% error. So we were off by about 12% in this experiment in which we found the density of zinc. Again, this is a formula that you need to memorize. Literature minus experimental divided by literature times 100. And now let's actually do some chemistry, not so much uncertainty, for just a couple slides. So hydrates. Hydrates are super cool. There are some ionic compounds that will actually bind to specific numbers of water molecules. So here's an example of copper sulfate. Here's our copper. Here's our sulfate polyatomic ion. Copper sulfite will always stick to water molecules. It is what we call hygroscopic. It's going to attract water molecules to it. It's actually going to attract 1, 2, 3, 4, 5. 5 water molecules will always be attracted to each unit of copper sulfate, copper 2 sulfate. And so I'm going to write this formula as CuSO4, that copper and then sulfate, copper 2 sulfate. I'm going to use a dot and I'm going to add the number of water molecules, 1, 2, 3, 4, 5. 5 H2Os. So this is telling me that each one of these copper sulfate units is attracted to, is bound to 5 water molecules. And I would call this copper 2 sulfate. And then these 5 waters are penta, penta for 5, hydrate for the water. Copper 2 sulfate pentahydrate. This one, I have barium chloride, so that BaCl2 bound to 1, 2, 3 water molecules. And so that 3 is shown there, BaCl2 dot 3 H2Os. And I would call this barium chloride Barium is not a transition metal. I don't need a Roman numeral in there. Just barium chloride. 3 for tri, and then hydrate. 3 waters, trihydrate. Barium chloride, trihydrate. One more chunk of practice, and then we will call this lecture done, my friends. All right, so looking at copper 2 sulfate heated over a Bunsen burner to determine the degree of hydration. So copper 2 sulfate is a compound that is a hydrate. It is attracted to water molecules. In this investigation, we're trying to figure out how many water molecules, what is that degree of hydration. So how we're going to do this, we're going to take some hydrated copper 2 sulfate, we're going to heat it up. It'll cause that water to evaporate away, and then we'll have dehydrated copper 2 sulfate. Our change in mass, we start at 4.99, and we're going to end up at 3.19. To find that change in mass, we're just going to subtract. So 4.99 minus 3.19, we're going to get 1.80 grams. 5.01 minus 3.20 is going to give us a change in mass of 1.81 grams. 4.97 minus 3.16, again 1.81 grams. Let's figure out our uncertainty here. Because I'm subtracting, I'm going to add my uncertainty. So plus or minus 0.01 plus or minus 0.01 is going to give us plus or minus 0.02 grams. So when we add and subtract, we can just add the uncertainties. Our uncertainty will be plus or minus 0.02. So now let's look at some questions. Determine the average mass of the dehydrated copper 2 sulfate. That's these values here. Average is easy. We're just going to add these up and divide by 3. So 3.19 plus 3.20 plus 3.16 divided by 3 is going to give us, let's see, that's 9.55 over 3. 3.18 is going to be the mass. Uncertainty, happily, when we find averages, we also just average the uncertainty. And the average of 0.01 and 0.01 and 0.01 is, interestingly, 0.01. So the average mass of the dehydrated copper 2 sulfate is 3.18 plus or minus 0.01 grams. Let's do the same thing for our average change in mass. That's these values. So 1.80, 1.81, 1.81. Add those up and we get 5.42. Divide that by 3 values and we have 1.81. Again, that uncertainty, we're just going to average 0.02 times 3 divided by 3 gives us plus or minus 0.02 grams is that average change in mass with uncertainty. Next question, we want to determine the percent relative uncertainty of the change in mass. Percent relative uncertainty, we're going to take the absolute uncertainty and divide it by the data times 100 to turn it into percent. So I'm going to take that 0.02 that's here. 0.02 is my absolute uncertainty. Divide it by my value, 1.81. 1.81 times 100 will give us our percent uncertainty. So decimal looks like 0.011 times 100 will be 1.1%. We were not off by very much at all. To figure out the degree of hydration of this sample, the degree of hydration. So we're finally going to do some stoichiometry, my friends. How excited are we? So when we're looking at those formulae, like magnesium sulfate is a heptahydrate. There are 7 waters for every 1 magnesium sulfate. This 7 is telling me that the mole ratio of magnesium sulfate to water is 1 to 7. So what we're going to do is figure out the number of moles, not of magnesium sulfate, but of copper 2 sulfate in this example. We're going to find the number of moles of water, and then we're going to figure out what even is the ratio of those two. So step number 1, let's find the number of moles of copper 2 sulfate. So our dehydrated copper 2 sulfate, that average mass was 3.18 grams. 3.18 grams. I'm going to turn those grams into moles. So copper 2 sulfate, CuSO4, CuSO4. Let's see, copper plus sulfur plus oxygen. Copper is 63.55, sulfur is 32.07, oxygen is 16. We add those all up together, 4 oxygens, and we get a grand total of molar mass 159.72 grams per mole. Grams on top and bottom cancel out, and so we are left with moles. We have 0.0199 moles of that copper 2 sulfate. We do the same thing for our water now. So the water is that change in mass. So the difference between the hydrated and the dehydrated is the water. So I'm going to take that mass of water, 1.81 is our average grams of water. Divide that by the molar mass of water. Hydrogen is 1.01, oxygen is 16. Add those up and we get 18.02 grams per mole. Again, grams cancel out top and bottom. We're left with moles of water. We have, calculator says 0.100 moles of water. So our ratio of moles of water, 0.100, to moles of copper to sulfate, 0.0199. This is super messy. What we're going to do is divide both of them by the smaller of the two values to get them to round up to some whole numbers. So when I divide both of those by the smaller of the two, which is 0.0199, copper to sulfate is a 1, and then water turns into 5. So we're going to round that to 5 H2Os. Our degree of hydration is 5. We have 5 water molecules for every 1 copper 2 sulfate. And if you're not super excited about that math, don't even worry. We're going to do it again in class. So, objectives accomplished. We did it, my friends. We reviewed accuracy and precision. Accuracy, we're getting the right values. Precision, we're getting the same values over and over. They may or may not be right. We reviewed sig figs and all those rules. We outlined experimental errors. Experimental errors can be systemic or random. We defined and then calculated so many absolute and relative uncertainties. Absolute is what the scale or the thermometer says, plus or minus something. Relative is going to be that absolute uncertainty divided by our piece of data. We calculated percentage error, absolute value of literature minus experimental values over literature values times 100 to turn it into a percent. We reviewed hydrates. There are some ionic compounds that just stick to water. We calculated that degree of hydration, and that's a lab we're going to do in class. So if you didn't quite catch it, no worries, my friends. We'll do it again. Good work today. It was a lot.